Related rates. Okay? This actually probably goes more along the lines with implicit differentiation, which we did when we're doing implicit differentiation.
Yes.
Okay, all the dy over dx's and all that stuff. Okay, we're going to use implicit differentiation, but we're going to use it with respect to time. Okay, because remember, derivatives are rates of change.
Yeah.
Okay, so if you're talking about the rate at which I run, it's what feet over minutes or whatever. How many feet can I run per minute? Not very many. Okay, so all of this differentiation you're going to do with respect to time. Okay, so you'll have like a dx dt or a dy dt or a dr dt. Okay, now here are the steps for solving. Related rates, the common thread is some equation that relates, hence related, two or more quantities that are all changing with respect to time. Okay, and here are your little kind of steps for solving. All right, identify all given quantities and quantities to be determined. Make a sketch and label the quantities if appropriate. Sometimes, again, a picture is worth 1,000 words. All right, step 2, set up an equation involving the variables whose rates of change are either given or are to be determined. Step 3, differentiate implicitly with respect to time. All right, and then substitute all the things you know and then solve for the remaining rate, which is what you're going to be looking for. All right, so let's start off with an easy problem. Example 1. Okay, so again, example 1 at some time. All right, suppose that x and y are both differentiable functions of t and are related by the equation y is equal to x squared plus 3. Okay, the thing on Khan Academy that I told you not to do, the parametric functions, it's kind of related to this as well. Okay, it's kind of related to this as well, except they actually give you an equation x is equal to something with t in it. Okay, here we don't give you the function, we just give you a function, but they're changing with respect to time. All right, so I know y is equal to x squared plus 3. What's the shape of that graph?
Parabola.
Parabola has been shifted up 3, very good. All right, I want to find dy dt, or in other words, what is the rate at which y is changing when x is 1, given that the dx dt, the rate at which x is changing with respect to time is 2, when x is equal to 1. Okay? So this one's actually pretty straightforward because they gave you an equation. Other ones you're going to have to set up an equation, which is kind of the hard part. So here we have this equation is our equation relates everything. I know y is equal to x squared plus 3. All right, and let's come over here and figure out the stuff that they gave us. All right, the given. All right, they gave us what? X is equal to 1. When x equals 1, I want to know, and also they gave us what? dx dt. They told us that was 2. All right, and then they told us x is 1 again, but hey, we already have that, yes? And we're trying to find what?
dy.
Find dy dt. Okay? Now, sometimes it might be beneficial, even though they just gave you x is equals 1, sometimes it might be beneficial to figure out what y would be at that time as well, which you could easily just plug in and say, hey, if I plug 1 in, what's y? 4. Okay? I don't think we need it on this one, okay, but sometimes you might. Sometimes it's not given to you, but you can find it by plugging it in. All right, so once we have our equation, we know our given stuff. Okay, we're going to take the derivative implicitly. Okay, so for every variable, you take the derivative like you would normally do, and then just put d, that letter, over dt. All right, so what's the derivative of y? All right, y prime. If it was x, it would just go down to 1, right? Okay, but since we're doing implicitly, we're going to write this as dy dt. Okay, and do go ahead and write it like that, because y prime, what are we taking the derivative with respect to? All right, we're taking it with respect to time. All right, what about x squared? How do you take the derivative of x squared? 2x. All right, but since we're taking with respect to time, we also need to say times dx dt. Okay, for every variable, once you do the derivative, you also put in d, that letter, over dt. Every single time. No matter how many variables are there. All right, and then finally, what's the derivative of the plus 3?
0.
0. So do I need to even put it?
No.
No. Okay, so here is my related rates. This was related. These are now rates, and they're related. And now I just plug in everything I know. I'm looking for dy dt. That's what I'm looking for, yes?
Yes.
All right, so I don't know that. All right, do I know x?
Yes.
At this particular time, it's 1. So we know it's 2 times 1. And we know dx dt is what?
2.
2. So if we multiply that together, we know that our dy dt, the rate at which y is changing when x is changing at 2 and x is 1 is 4. All right, questions on that? Okay,
Please tell me it doesn't get harder.
it does get harder.
It gets way harder.
Okay, this is, hey, here's an equation, do. Other ones, here's a problem. Figure out an equation and then do.
it.
Oh my gosh.
Okay, so there's example 1.
It's okay.
All right, example number 2. Example number 2. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Okay, ever dropped a pebble in a pond?
Not a common one.
Ever dropped anything in water?
Yes.
Right?
That's not a common.
Okay. If you have a still water and you drop something and it ripples out in concentric circles. Okay. All right. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? All right, so what, right? Okay, so let's figure out what's given to us. Okay, the first thing that's given to us is the outer ripple is increasing at what? 1 foot per second. Or in other words, the radius is changing at 1 foot per second. So is it increasing or decreasing? Increasing, so that would be positive or negative? Positive. You'll see some on the Khan Academy where it says, hey, something's decreasing. Something's decreasing, it's going to be negative. But in this case, we know the rate at which the radius is changing, the dr dt, is equal to a positive 1 foot per second. All right, they also tell us what?
The radius
The radius is 4 feet. All right, so the diameter would be 8, but I don't think I need that, possibly. All right, and then finally it says, what rate is the total area of the disturbed water changing? All right, so our find is going to be what? The rate at which what is changing? Area. So that's going to be dA dt. That's what we're trying to find. Okay, so we have some given, we know what we're trying to find. Now the question is, hey, we needed some kind of equation that relates all this stuff. Okay, but let's look at the very beginning. A pebble is dropped into a calm pond, forming ripples in the forms of what? Circles. If only I knew a formula that related radius and area. Oh, we do know that one. Area is equal to pi r squared. Okay. Now we know the radius, we don't know the area. It turns out on this one we don't need to. Okay. Because of the way the derivatives work out. All right, but we have our equation, and now we take the derivative implicitly. All right, so for A, it's just like A, it's just like X. If you take the derivative of a variable, you just get what? 1. But then you also need to talk about dA dt. So technically this is 1 times dA dt. All right, over on the right-hand side, I've got pi r squared. Okay, well, all right. Okay, product, chain, let's see.
Don't you treat R as if it's an X, so it's just product?
All right. Well, it's actually,
Isn't pi Yeah, it's just a number.
Pi is just a number, so it's just going to be a regular power rule with a coefficient in front. Okay?
You guys.
Pi is not a variable. Pi does not change. Pi is 3.1415, blah, 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 blah.
9.
Okay? So pi is just a number. So this is just like if I had like 4x squared. The 4 is just there.
Ah.
So that means that
But you multiply
circumference
2
is the
times.
derivative of area of the
It
circle.
is actually. Yeah.
Oh my gosh.
Wait,
All right.
Whoa.
So if I take the derivative, okay, r is the only variable. All right. So if you take the derivative of r squared, what do you do with the 2?
Bring
Bring it down, multiply by the coefficients that's already there. So that's 2 pi r to the first. All right, but since we took the derivative of r, we also need to write in dr dt. Okay, so the derivative of the area is the circumference times the rate of change of the radius. Okay, now we plug in. Okay, what it was given. We know dr dt is what?
1.
1, and we know the radius is 4. And that's all we need, right?
Yeah.
So we know dA dt is equal to 2 pi times our radius, which we said was what? 4 times our rate of change of the radius, which is 1. So we know that our rate of change of the area
8 pi.
is 8 pi square feet per second. Okay, square feet per second because, hey, this was, the 4 was feet, and the 1 was feet per second, so feet times feet gives me feet squared. Which, hey, it's area, it should be something squared.
You said it's like awful. Well, it's I can find the diameter circumference, but that probably doesn't matter. Is that like a lead on this?
Say that again.
Like when you were going through the college, like, well, I can find the diameter and the circumference, but I don't think that matters. Does that lead on that it would matter?
Well, it still really doesn't matter. Do I really care what the circumference is? No, it is. It does turn out to be 8 pi in this case, which is our answer. But that's not always going to be the case. That just so happened because our rate of change was just 1. All right. Questions on that? Still not too bad, right?
Nah.
Just wait. Example 3.
Oh my gosh.
All right, an oil tanker. Okay, oil tanker has an accident and oil pours out at a rate of 150 gallons per minute. Suppose that oil spreads onto the water in a circle at a thickness of 1/10 of a, I think that's an inch, right?
Yeah.
Okay, 1/10 of an inch. I think 2 is inch, 1 is foot. All right, given that 1 cubic foot is equal to 7.5 gallons, determine the rate at which the radius of the spill is increasing when the radius reaches 500 feet.
They gave us a lot of stuff.
All right, so let's write down what we know. Okay, if you ever have no clue what to do, just look and see what we know and go from there. All right, it should be increasing, not increasing, sorry. All right, so let's see. We know that the rate at which the oil pours out is what?
150 gallons.
150 gallons per minute, right?
What is that? What is that variable? DR over DC?
All right, well, what is gallon? That's what?
That's milk.
Is that a
No way.
No.
what kind of measurement is that? Volume.
That's it.
Oh,
I was the right choice. No.
All right, so this would be dV dt, the volume, which we're going to have to change that in a second. Okay, we know that what?
Thickness.
Thickness.
One-tenth of
Okay, so I'm going to say my height, okay, my thickness, my height is 1/10 of an inch. Is that changing?
No.
No, that is a constant 1/10, yes? All right, and then they also gave us this little fact right here. 1 cubic feet equals what? 7.5 gallons.
Hey.
Yeah, I think we're going to have to use a conversion in a second.
Oh.
All right. We want to determine the rate at which the radius of the spill is increasing. So we're trying to find what? Yep, DRDT. I heard somebody say it. When the radius reaches what? All right.
Let's do it.
All right, hopefully we do it right because this is the wrong one. All right. So, let's think about it. Is there some kind of equation we can get to relate all this stuff?
Volume equation?
I feel like,
It's going to be some kind of volume because we're talking about volume, yes?
yeah, if it was 50 cubic feet, that's
Volume.
Is
Is it just power
and then they talk about circles too. It's a cylinder. It's a
All
right.
She did say it
All right, Amelie, what did you say first? All right, it is a cylinder, very, very short cylinder. Okay, but it's what? It's in a circle, but it has a thickness. So it's a cylinder. And anybody know the volume for a cylinder?
2 pi r height. 2 pi r height.
All right, pi r squared h. Okay? Okay? You can kind of think about it like this. Okay, a cylinder is, the base is a what?
A circle.
Circle. Okay, so it's the area and then a whole bunch of areas stacked on top of each other times the height. So pi r squared, that's the circle part, and then the height is the height. Okay? If you wanted to find the volume of quarters, you had a whole stack of quarters. Well, it's 1/4 pi r squared, and then the height of it. Okay? So we have that formula. Okay? Huh. All right, well, let's go ahead and let's talk about those variables. Is the volume changing?
No.
Yes, the volume, we know that, right? We're going to have to change it a little bit. But is the radius changing?
Yeah.
As the oil's going out, what's happening to that circle? It's getting bigger, right? All right, the height is constant. Okay? So I'm going to put a little star by this. Height is a constant. Okay, because when we do our derivatives in a second, we're just going to treat h as a constant. Okay? If not, there's a what? A product rule going on. Okay? Which you could do that, but when you get the dh dt, the rate at which the height is changing, is the height changing?
No.
So it would be what?
0.
0, so that whole term would just do what? Go away. So we don't have to worry about it. All right, so let's take the derivative. All right, the derivative of v is going to be what?
dv over dt.
dv dt. All right, the pi and the h are just what?
Constant.
Constants.
So you just take the derivative of r.
Derivative of r, so it's going to be what?
2 pi r.
H.
Hey.
Almost.
Times.
No, DR.
All right, dr dt because that's the one that is changing. Okay, the h is a constant. All right, so can we just plug in?
No.
You got that height? You got the
All right, well, let's see. Our volume is in gallons per minute. Our height is in what? Inches, and our rate is in what? Feet. So we need all of those to be
same.
the same, yes? Okay, so before we plug it in, let's go. The volume, can we change that with feet?
Yes.
We know what? 1 cubic foot is equal to what? 7.5 gallons, so how do we convert?
150 divided by 7.5.
20, so
150 divided by 7.5?
21 and 3 over 7.
You can work it out.
Got a calculator. That's what?
21.
20. So this right here, we can actually rewrite this as 20 cubic feet per
Oh, 7.5.
minute, right? Okay? It's 150 gallons. How many 7.5s are there in 150 gallons? 20 of them by dividing.
Yeah.
So 20 cubic feet per minute is our dV/dt. All right, so that's in feet. Our radius is in feet, but our height is in what? Inches? Pretty sure that's inches, right?
Yeah.
Okay.
Yeah.
So we need to convert that to what? Feet?
Dang, that's like.
All right, so 1/10 of an inch
Divided by 12.
Oh my
divided by 12, because there's
Times 12.
It's divide.
That's
You
divide.
divide.
Actually, it is. Yeah, you're right.
God. Small big.
This ancient taught us.
All right. Okay, we got 1/10 of an inch, so if we multiply by 1 foot over 12 inches, our conversion factor,
One.
the inches go away, I'm left with feet.
120.
So 1/120th.
Yes.
Good.
So
Well,
many.
that's not.
Ancient taught me this same.
It's ages. Oh yeah. No, the homie.
All right, so we now have all of our given terms in the same unit of measurement, right, in feet? All right, so let's plug in. All right, we know that the dV/dt is what?
20 feet. Cube.
20 cubic feet per minute, right? We got 2, we got pi. We know our R is what?
500 feet.
500 feet.
Times 1.
And our height is 1/120th of a foot. And we still were looking for the dr/dt. All right, so let's multiply everything out on the right-hand side. Let's leave the pi in there for right now. So 2 times 500 times 1/120th. Is 8 1/3. As a fraction, that's what?
27. 25.
25.
Yep.
No, the answer is 25.
How about 26.199?
All right, 25 pi over 3. Okay. The numbers without the pi gave me 8.3 repeating, which is 25 thirds. Math frac, you can get in your calculator. All right. And then what measurement is that in? We got feet times feet, so that's what?
Feet squared.
Feet squared. And we still have the
dr/dt.
dr/dt. All right, and so how do we find the dr/dt?
Divide it over.
We divide
All right, we can either divide it over or we can multiply by the what?
reciprocal.
Reciprocal. Since it's a fraction, I would probably do that. So multiply by 3 over 25 pi. All right, well, we could do a little bit of reduction here, some canceling out. What will go into 20 and 25?
5.
5, making the 20 a what?
A 4.
4, making this a
5.
5. All right, so our dr/dt exactly is what? 12 over 5 pi. All right, and we had cubic feet, but we divided what? Square feet out?
So it's just
So 1 foot
per minute.
per minute. So our exact answer there is 12 over 5 pi. All right, which sometimes might be the answer. Okay? But if it was just a straight, purely mathematical problem, I would like that answer. All right, but this is a real life problem. If you told somebody, how fast is it changing? How fast are you running? Well, I'm running 12 divided by 5 feet per minute. Would that make much sense to you?
No.
No, so we probably want to do, just figure out what that number is approximately. All right, now be careful on this.
Would you put pi or just 3.14?
I would use pi, okay, but when I do, I'm going to say 12 divided by, and since there's 2 things here on the bottom, I'm going to put a parentheses, and then put the 5 pi. All right, so 12 divided by 5 pi with a 5 pi in parentheses. All right, and so the pi is second, and then the button right above the division symbol. So this is approximately what? 7.764 feet per minute. Okay, if you don't put the 5 pi in parentheses on the bottom, the calculator is going to say 12 divided by 5, and then multiply it by the 5. Okay, so the 5 pi has to be parentheses if you put it in your calculator.
We should do a video for it.
Okay? All right, questions on that one? A little bit more detailed, right?
Annoying.
Okay? And I believe on Khan Academy, they usually give you the relative formulas.
Yeah.
Or they've given you the formula like in a previous problem. If they don't. All right, example 4. Example 4.
25.
25 minutes, wow. All right. All right, air is being pumped into a spherical balloon at a rate of 4.5 cubic inches per minute. Find the rate of change of the radius when the radius is what?
2 inches.
2 inches. All right, so let's talk about our given.
Cubic inches per
4.5
minute.
inches.
Oh!
Cubic.
I'm sorry.
4.5 cubic inches per minute, right? That's going to be our what?
Radius.
Rate at which what's changing.
The radius volume.
Air is being pumped into it, into a balloon, so the balloon's what, getting bigger, so that's what, volume? So dV dt. It's also a cubic something, so that kind of tells you, hey, cubic is volume. All right, they also told you that the radius is what?
2 inches.
Radius is 2, and we're trying to find what?
The rate of change. So D.
dr dt, the rate of change of the radius.
What's DVDT?
The volume.
You scared me. He took my seat.
All right, so what's our formula?
4/3 pi r cubed. Wait, that's wrong.
I'm just trying to figure out what that last word was. All right, volume for a sphere is 4/3 pi r curve.
This is too.
Wow. All right, so we look at our equation. We have our only variables here are what? Volume and radius. And they're both changing, right?
Yeah.
The balloon is changing volume, so is the radius. So none of those are constant. But it's nice because we don't have to worry about a product rule. That's awesome. Can we take the derivative of that?
Yeah.
Derivative of v is going to be
DV.
dv over dt. All right, the 4/3 and the pi are just constants. So we really just got to worry about r cubed. All right, the 3 is going to come down, right? 12 thirds, which would be what? 4 pi r squared dr dt. Okay, the 3 came down, but since there was already a 3 on the bottom, that just what? Canceled out, leaving you with a 4 pi r squared dr dt. All right, and then plug in what we know. Our dv dt is what? 4.5 cubic inches. As a fraction, that's what? 9 over 2. Okay,
Why did you convert it? Oh, wait.
just so we can have an exact answer without fractions and decimals going on.
It'd be like this.
All right, what's our radius?
2.
2, so we have 2 squared.
That's false.
That is 4. All right, so we have 9/2 on one side, which that's in cubic feet, yes? Over here, this is a what, square feet? Cubic feet per minute. This is square, full inches, yes, I'm sorry. Cubic inches per minute, cubic inches, or square inches.
Yeah.
So we didn't have to do any conversions here, thankfully. All right, this side, 2 squared is what? 4. 4 times 4 is
16.
16.
Okay.
All right. And then what do I need to do with the 16? Divide it over.
This is 16 or 16 pi.
The whole thing, 16 pi. All right, so dr dt exactly, when I divide the 16 pi over, it's going to give me 9 over 32 pi. And that's in what? Inches per
Squared. Wait.
Okay? Divided by 16's pi. So where's the 16 by pi get?
On the bottom.
On the bottom, which already had a 2. 2 times 16 is
32.
so 32 pi on the bottom.
We need to go ahead and simplify that out.
All right, so simplify that out. Make sure you put the bottom in parentheses.
0.88.
Can you go on simplify or no?
Can you simplify it?
Oh, no, never mind.
You would if you could, but you can't. So you won't. All right, so this is approximately what?
0.0890.
Oh, never mind.
Okay, my calculator gave me 0.0895.
Yeah.
If you go to 3 decimal places, that would be the 5 makes the 9 go up to 10, which comes over to the 8.
Oh, so you want to do it. So go over 3.
Do 3 places. Okay. My calculator gave me 0.0895, so technically there's the 3rd place. But the 5 makes the 9 go up to 10, which shoots a 1 over here to the 8, making 0.0. All right, questions on this first half of the notes?
That's easy.